What's up, guys? Today I'm doing a video on margin of error and confidence intervals. And we're focusing on margin of error to confidence interval for proportions. There's another margin of error and confidence interval that we're going to look at for mean. And conceptually, they're very similar. It's just a question of whether you're measuring the mean of a data set or the proportion of a population. We'll talk more about that later. But the basic definitions are the same. A margin of error is an interval describing how accurate an estimate of a parameter is. Again, the parameter could be population proportion or sample proportion, or it could be mean. The confidence interval is basically just whatever your estimate is plus or minus the margin of error. Okay. And we'll do an example. Hopefully it makes more sense. But it's based on a confidence level. So a certain percentage of likelihood that you want to have. So, we'll see an example in a minute. The confidence level is the probability that a margin of error or a confidence interval is accurate. Okay. And this is the formula for confidence interval. Okay. Confidence interval, here's the formula. And this is the only formula I really wanted to put on here because, and it's on your formula sheet, but this formula contains the formula for the margin of error. And this is what I mean when I say the confidence interval is an estimate plus or minus the margin of error. P hat would be your estimate in this case. Okay. Maybe I think the population proportion based on my sample. So my P hat, maybe it's 65% plus or minus whatever the margin of error is. Maybe the margin of error is 3%. So it'd be 65% plus or minus 3%. That might be my margin of error. And then I would also have assigned to that some confidence level. I might say I'm 95% certain that the population proportion is 65% plus or minus 3%. That's kind of how it's used. We're going to look at an example in a minute. I know that's a lot of numbers being thrown at you, a lot of words. In this formula, we know what most of this is. In fact, this right here is what we just talked about recently. This is the SEP. Okay, this is the standard error of the proportion, which really, remember, this is just a standard deviation for that distribution. Or if I take lots and lots and lots of samples, I get this distribution of samples. Okay, this describes the standard deviation of that curve. Okay, what is the standard deviation of the curve? This number here is the critical value. And I'm going to do a lot of explanation about what this number is because it's very important. I think a lot of times people sort of learn this just as some number you multiply by, and they never really understand why. And if you have to do that, that's fine. But I would much rather you understand what this is and kind of why we use it. Okay. So the critical value is a number. It's the number of standard deviations, or the z-score, based on a given confidence level. Okay. And I've got a whole big explanation for that. But taken together, when you multiply the critical value times this, which is just SEP, this gives you the margin of error. Okay. Saying, I think the proportion is whatever p hat is, plus or minus some margin of error. I'm pretty sure it's in between these two numbers. It's between p hat plus this number and p hat minus this number. And somewhere in between there is the actual population proportion. Okay, so I have a table here, and this is on your formula sheets, and it's describing confidence level and critical value. Now remember, the critical value was a number in our formula here, and it has something to do with the margin of error. The margin of error is the standard deviation, really it's the SEP, the standard error of the proportion, times this critical value. And based on that, that's going to tell me the margin of error. In other words, how much to add or subtract to p hat to say within some degree of certainty that the actual population proportion is in between those two numbers. Okay, maybe I think if p hat is 65, maybe I can say I'm 99% certain that the actual proportion is somewhere between 60 and 70. Okay, that would be a margin of error of 5% because I'm adding or subtracting 5% from what I think the proportion is. Okay, if I was willing to be a little less certain, I can make that more narrower. I can be more specific. Let's say, well, I can say with a 90% degree of certainty that it's actually somewhere between like 63 and 67%. Okay, so the less confident I am in my answer, the narrower I can bring in my ranges on that estimate, and it'll hopefully make more sense once we see an example. But I want to draw some attention to a couple things here. Notice, again, as I said, as the confidence level gets higher, as I'm more confident in my range containing the actual population proportion, this number gets bigger. If I'm less confident, this number gets smaller. Well, going back to the formula, the smaller this number is, the smaller this whole part is going to be. The margin of error is going to be smaller. So the smaller the critical value, the smaller the margin of error, which means I'm adding or subtracting less, which means my lower and upper bound estimates are going to be closer together. Okay. So I can have a very narrow range and be 50% confident, for example. If I want to be 99% confident that my intervals include the actual proportion of the population, then I've got to cast a pretty wide net, in other words, and that's going to make this number a lot bigger. All right, so here's another way to think about this. Where are these numbers coming from? Okay. Look at, this is the normal distribution, the empirical rule, right? 68%, 95%, 99.7% for 1, 2, and 3 standard deviations. Normally we talk about from the mean, but since we're talking about proportions here, remember the population proportion is in the middle. This goes back to the SEP lesson we did when we talked about how if I do lots of samples of proportions, that they will tend to fall into a normal distribution, with the center being the actual population proportion, assuming I do enough samples and that the sample size is big enough. Well, let's point out a couple things here. There's a 95% here and there's a 95% here. There's actually not a coincidence there. There's a reason for that, okay? Within 2 standard deviations on the normal distribution, in the empirical rule, within 2 standard deviations, you find 95% of the data, usually. Well, that empirical rule, as we remember, is kind of an estimate. It's not exact. It's actually not 95%. Or another way of saying is it's not really 2 standard deviations. It's actually 1.96 standard deviations, okay? So if I was to take a distribution like this, and let's say I'm just going to randomly pick a number out of here, okay? What's the likelihood that the number I pick is going to be within 2 standard deviations? It's 95%, okay? Another way of saying is if I want to be 95% confident that the number suppose I'm going to cast a lower and upper bound on here. I'm going to set some lower limit and some upper limit, and I'm going to say I'm pretty sure that the population proportion is in between there. Well, how certain can I be? Keep in mind that this is the population proportion here. How certain am I that the actual population proportion is in between those 2 numbers? Well, since this would be 95% of my data, I can be 95% confident that in between that lower and upper bound limit, the actual population proportion is going to be in there. All right, finally, let's do an example. And hopefully all this stuff makes more sense. And maybe after we do this example, go back and watch the other stuff again, because sometimes you just got to see it in action to really understand what somebody's talking about. So we have this bag of marbles. A sample of 30 marbles from a bag had 14 green marbles. So maybe there's a bag of 1,000 marbles. I don't know how many, but we drew 30 marbles and 14 of them were green. Find a 95% confidence interval for the proportion of green marbles in the bag, okay? So what we're talking about here is we want to come up with some estimate of what proportion of marbles in the bag are actually green. You would think, hey, we took a sample of 30, so 14 out of 30, that must be the percentage of marbles in the bag that are green. Well, remember, that's just one sample, okay? One sample, it's probably pretty close, probably, and that probably is the key word. How probably, how likely is it that that actually is the population proportion? It's our sample proportion, right? So that's p hat. We just found p hat right there. P hat is 14 out of 30. So in this sample, 14 out of 30 were green. We'll see what that is. 14 divided by 30. It's about 0.47. So about 47% of the marbles in our sample were green. Does that mean that 47% in the bag are green? It's probably pretty close, but we're more concerned with how close are we? And that's where the confidence interval comes in, okay? So the next thing we need to find is we need to find the standard error. We need to find the standard deviation. If I were to do lots and lots and lots of samples of this, and I were to get my distribution here, maybe that 0.47 is not really, maybe if I did lots of samples, some other proportion would emerge as being closer to the actual proportion in the bag. What's the standard deviation of that curve? Remember, that's the SEP. SEP is the square root of p hat, 0.47, times 1 minus p hat, which would be 0.53, So again, remember, they always add up to 1, divided by the sample size, which in this case is 30. So let's put that in our calculator, see what we get. I'm going to do the square root of, hit the fraction button, 0.47 times 0.53 divided by 30. It's about 0.091. Okay, that's our SEP. Okay, so the next thing we need to do is we need to figure out, looking back at our formula, okay, we know this now. Okay, we found p hat, which we had to use since we don't know the actual population proportion. We looked at our, we found this whole part here, which is the SEP. The next thing we need to figure out is what's the critical value, and that's based on 95%. They said they wanted a 95% confidence interval, okay? So if I were to write the margin of error is plus or minus, really the margin of error is this part of the equation, right? So it's plus or minus the critical value, and that's what we need to find. What is the critical value? I wanted 95% confidence. So the critical value is 1.96. So I'm going to say plus or minus 1.96 times, and normally I'd put that base square root. We already found all this stuff, right? So we'll just write 0.091. We already found that. Okay. And this comes out to 1.96 times 0.091, 0.178. Okay, so then what is the confidence interval? The confidence interval is simply p hat 0.47 plus or minus our margin of error, 0.178, which gives us two numbers. Plus or minus means it's two numbers. Then you do this plus the margin of error and p hat minus the margin of error. So 0.47, I'll do minus first, minus 0.178, 0.292, and then if I do 0.47 plus 0.178, I get 0.648. So this is our confidence interval, okay? I can say I am 95% certain that the proportion of green marbles in the bag is between 29.2% and 64.8%. Well, that's a pretty wide margin, right? It's like, yeah, no duh. That's, of course, it's somewhere between there. We found a proportion of 47% in our sample, and you're saying that the actual proportion in the bag is between 29 and 64%. Well, that's a very wide margin. So yeah, it's pretty certain. Well, again, we wanted 95% confidence. Okay. What if I was willing to be less confident? What if I said, well, maybe I just want to be 90% confident? Okay, because 95% confidence is pretty high. Like that's saying I'm pretty sure, 95% sure that the actual proportion of green marbles in the bag is between 29% and 64%. Well, if I was willing to be a little less confident, and I'll do it all in one step this time. Instead of finding each part, I'm going to do it all at once. So a confidence interval, and again, this will be for 90%. Okay, 90% confidence interval. What would that look like? This was 95%. Let's just put the formula all in at once, and so we can see that you can actually do all of this at once. P hat is still the same, 0.47, plus or minus. I'm going to do the critical value, which I got to look up. 90% in my table, 90% is 1.645 times 0.47, 0.53. And I know that we know some of this already, but I just want to kind of show you how you can type the whole thing in at once. So instead of finding the little parts, I just kind of put the whole thing in at once, okay? And let's see what that is. I'm going to do 0.47 minus 1.645 times the square root of 0.47 times 0.53 divided by 30, 0.320. And then on the upper end, I'm just going to go up here and I'm going to change that minus to a plus. I'll scroll back and change that minus to a plus. Press enter. and 0.619. So it's really about 0.620. It's the correct way to round that. Okay, so it wasn't a huge difference, but we did make our interval a little narrower. Okay, so instead of saying I'm 95% sure that it's between about 29.2% and about 64.8%, well, I could say I'm 90% confident, which means I'm a little less confident, but I'm still pretty confident that the proportion of green marbles in the bag is between 32% and 62%. Okay, you could go as low as you want to go. If I was willing to go to a 50% confidence level, it would be even smaller than this, right? So I'm only 50% confident here. So I'm kind of like it's about a 50-50 whether I'm right or not, but I think I'm 50% confident that between 40.2% and 53.8%, that's actually the true proportion of green marbles in the bag. Okay? So if I want to make the margin narrower, I got to lose some confidence. I can't be quite as confident in my answer. If I cast a really wide margin, say I'm pretty sure it's between like 10% and 90%, well, yeah, of course, that's a pretty easy thing to guess. I can say that with a really high degree of confidence. The other way that you can increase your confidence, or that you can make the margins more narrow, would be to take a larger sample. Okay, notice that in this formula, the larger this number gets here, remember, the bigger a number at the bottom of a fraction gets, the smaller that whole fraction gets. And the square roots is smaller still. And so the bigger this number gets, the smaller the whole entire margin of error is going to be. Okay, so if you want to be more confident in your prediction, you need to take a bigger sample. If I had taken 100 marbles instead of 30, then there's much more likelihood that p hat, that proportion from the sample, is closer to the actual proportion from the population.